Here we have the notes for Section 5, Parametric Relations and Inverses. So here down here we have the definition for relations defined parametrically. So that means that you're defining x and y in terms of a third variable t, and that t is referred to as the parameter. So if you look at example 1 there, this is an example of what it looks like. So you have two equations, x equals and y equals. Both of them have t on the right-hand side, where t is any real numbers. So the first one there says find the points determined by t equals -3 through +3. So what we're going to do is we're going to have a modified t table. So we have 3 columns, one for t, x, and y. So t is going to run from -3 to +3. So to find my x values, I'm going to take my t's and plug them into the x equation. So it's going to be +1. So -3 + 1, -2 + 1, -1 + 1, so on and so forth, all the way down the list. So take your t's, plug them into the x's, and that gives you your x column. Repeat the process for the y. So I'm going to take my t values, plug it in here, get my y values. So I'm going to have, this is going to be, if I plug -3 in, that's -3 squared is 9, minus 6 is 3. If I plug -2 in, that's 4 minus 4, which is 0. If I plug -1 in, that's 1 minus 2, that's -1. If I plug 0 in, that's 0. If I plug 1 in, that's 3. If I plug 2 in, 2 squared, that's going to be 8. If I plug 3 in, that's 9 plus 6 is 15. So the second part here says find the algebraic relation between x and y. So to do that, you start with your two equations. And what you're going to do is you're going to pick one of them to solve for t. It doesn't matter which one, so choose the easier one. So in this case, this equation is easier to solve. So to solve for t, I need to move the 1 across. Gives me that. Now what I'm going to do is I'm going to take, since I know what t is equal to, I'm going to take this equation and put it in for those t's. So y equals x minus 1 squared. So replace that t with x minus 1 plus 2 times x minus 1. Replace that t with x minus 1. So now you have an equation in terms of only x and y. Now the second part where it says is y a function of x, you actually look back up at your t table. If no x values repeat, it is a function. So this one would be, yes, it is a function. And the last part here says graph the relation, so draw on some axes. So that's your plotting your points from up above. So the first point is at -2, 3, and then we had -1, 0, and then 0, -1, then 1, 0, then 2, 3, then 3, 8, and the last one's going to be off, so I'm just going to leave it alone. So if you notice, though, there's no arrow here or there because I have endpoints. This graph doesn't continue on forever. It only exists between t equals -3 and t equals +3. All right, example 2. So these are the same things, except we flipped the x and the y equations. So t, x, y. So -3, -2, -1, 0, 1, 2, 3. Now I'm going to cheat and look at my previous column. So it went from 3. Okay. So the x column is the y equation, so it's going to be the same thing again. So at -3, that's going to be 3, 0, -1, 0, 1. Nope, that's a lie. 3, 0, -1, 0, 3. I'm just copying the y down, the y column from the other one since the equation switched, the column switch. So 2 was going to be 8, and this is going to be 15. And then here it's going to be -2, -1, 0, 1, 2, 3, 4. So find the algebraic expression. So I've got x equals 2t, y equals t plus 1. So now this time that one's easier to solve. So I'm going to solve my y equals equation. So y minus 1 equals t. I'm going to take this equation and put it in for the t's over here. So x equals y minus 1 squared plus 2 times y minus 1. And then for graph the relation, the is it a function part? If you look at my x column, I have x's that repeat. So this is not a function. Because here's 3 twice, 0 twice. Okay. So to plot the points, we've got over 3 down 2, so 3, negative 2, 0, negative 1, negative 1, 0, 0, 1, 3, positive 2, 8, positive 3, and then the last point's way out here. So there's my graph. So the other way to check actually for functions, if you look at the graph, remember if there's a vertical line that crosses more than once, it's not a function. And this, since it's part of a sideways parabola, there is a vertical line here that crosses more than once. All right, so down here we've got inverse relations and the inverse functions. So an inverse relation just reverses the x and y values. So this example here, examples 1 and 2, those are inverses of each other. The x and the y's reverse their order. So up here at the top, you've got what's referred to as the horizontal line test. So the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation in at most one point. So functions may have inverses, but those inverses may not also be functions. That's what the horizontal line test is. So vertical line tests if the original equation is a function. The horizontal line test tests whether the inverse will also be a function. So if you look at these 4 graphs, example 3, which of the graphs below are graphs of relations that are functions. So that's of these, which ones pass the vertical line test. So 1 passes the vertical line test and 4 passes the vertical line test, because there are no vertical lines in 1 and 4 that cross more than once. Which of them have inverses that are functions? So that means you have to pass the horizontal line test. So that would be 1, 2. There are no vertical lines that cross more than once, and that's it. Because here, over here, 4, there are horizontal lines that cross more than once. Equation 1 here is an example of a one-to-one function. It is a function, and its inverse is also a function. So down here, we have how to find the equation of the inverse. So we have f of x equals x over x plus 1. So your first step is you replace f of x with y. So it looks like that. Second step is you switch the variables. Y's become x's, x's become y's. So it looks like this. Now, third step is kind of generic. It just is solve. So to solve this, I'm going to multiply both sides by y plus 1 to get it out of the bottom here. So on the left, I'm going to have x times y plus 1. And on the right, I'm going to have just y. So I need to distribute my x. xy plus x equals y. So now I want to get all terms that have y's by themselves. So I need to move this term to the right. So we're going to come up here. So x equals y minus xy. Since these terms both have y's, I can factor that y out. So x equals y, quantity 1 minus x. And then to get y by itself, I can divide this whole parentheses across. So x over 1 minus x is equal to y. And to write it as an inverse, you switch the y to the f negative 1 of x. So those two equations will be inverses of each other. Okay, example 5 just refers to it in terms of a graph. So this is just using the fact that you flip the x and y values. So the first x becomes the new y, y becomes x, so on and so forth, which is the same thing as reflecting across the line y equals x. So here, if you look, there's these 2 points here. That point is at negative 1, 0, and that point is at 0, 1. So do the reflection, I'm just going to switch their x and y. So this point will now be at 0, negative 1 down here, and that point will now be at 1, 0 right there. So it's going to mirror it, something like that. Well, that's pretty sloppy, but so that line there is y equals x. So that's the line it's reflected across. Okay, down here we got the inverse composition rule. This is how you've checked to see if your inverse is correct. If you form a composite between two functions and you get x out, just x, that means they are inverses of each other. So if a function f is one-to-one with inverse function g, if and only if these are true. So what that happens is, so here's my f, here's my g, so I'm going to find f of g. So that means take my g equation and plug it into my f equation. So the cube root of x minus 1 cubed, all of that replaces just the x, so the cube's still there, plus 1. So here, so if I keep working this out, the cubed cancels the root, so x minus 1 plus 1. The negative 1 and positive 1 cancel out, so I'm left with just x. You can do the reverse as well, g of f. So that means I'm going to take the entire f equation and put it in for that x. So x cubed plus 1 minus 1. So that x cubed plus 1 replaces just that x. So here, plus 1 minus 1's cancel. So we have the cube root of x cubed. Cube root and cube cancel, so just x. So the functions are inverses because they're composites simplified to just x. And the last one here, show that f of x is equal to this, has an inverse function, and find the rule for that. State any domain restrictions of f and f prime. So first step, switch x and y. Second step, trade the variables. Third step, solve for x, or solve for y, sorry. So square both sides. X squared equals y plus 3. Y equals x squared minus 3. So that becomes the inverse is equal to x squared minus 3. So it says, and find a rule for, or state any restrictions for the domains. So we have to check the domains for both. So for f, the domain, it has a square root, so the stuff underneath the square root must be greater than or equal to 0. So x must be greater than or equal to negative 3. For the inverse, this has no square roots, no fractions, so the domain is all reals. And that is the end of this section.